Now that we know what it means to take the composition of two functions, we're going to use that understanding to help us understand inverse functions. So first, we're going to give a model for inverse functions, as we always do. Then we're going to demonstrate how that model works on an example. We're going to use the model to help motivate the formal definition of inverse functions. And then we're going to test this definition on the example that we worked out with the model. All right, so first, the model that I like to use for inverse functions, I call it the Sisyphus model. If you don't know who Sisyphus is, look up some Greek mythology. Anyway, given a function f, the inverse function, f inverse, is the function that undoes f. So, in other words, f works really hard to do something to an input, and then what f inverse does is ruin all of f's work, brings that output right back to the input where it started. So if you want to see how that looks with our action model, so we start with an input, we do f to it, we do some action of f, then with whatever that is, we get f of x. Then we take that f of x, we do the action of f inverse, and that brings us back to our original input. So as an example, we have our old friend f from the real numbers to the real numbers, f of x equals 2x plus 3. So remember, for x, we do f to x to get 2x plus 3. And now the idea is, what kind of actions do we have to do to get back to x? Well, the first thing we want to do is to get back to x is to subtract that 3. That'll get us closer. When we subtract 3 from 2x plus 3, we're back to 2x. And then all we have to do then is divide by 2 to get back to x. So the two actions that we have to do to get back to x are, we have to subtract 3 and divide by 2, and those are going to be the actions of f inverse. So we're going to first subtract 3, then we're going to divide by 2 to our input. So for the computations we did above, our input was 2x plus 3, but for f inverse, that input is just going to be plain old x. Now, if we take x and subtract 3, we get x minus 3. And then if we take that x minus 3 and divide by 2, we get x minus 3 all divided by 2, which means that f inverse of x is equal to x minus 3 divided by 2. So now let's see if we can use that to give us a formal definition of inverse. Right now we're using our intuition, we're using our models, which is fine. It turns out to give us the right answer, but we do need, for logic's sake, to have a formal definition. So what happens is we do x, we do the action of f to get f of, and then we do the action of f inverse, and that takes us right back to x. So we start with x. When we do the action of f, that gives us f of x. Then we take that f of x and do the action of f inverse to that to get f inverse of f of x. In other words, we're taking the composition of f and f inverse. And what that's supposed to equal when we get to the end is x. Now, we need to be fair. If f inverse can ruin all the work of f, it's only fair that f should be able to ruin all the work of f inverse. So if we're going to start with x and we do f inverse first, and then we do the action of f, that should take us back to x. So we start with x, we do f inverse to get f inverse of x, then we do f to get f of f inverse of x, and that should get us back to x. And that gives us our definition of inverse. So we should have, if everything is as it's supposed to be, f inverse of f of x equals x, and f of f inverse of x equals x. Last formal issues that we have to take care of course, we have to worry about the domain and the codomain. Right now that we're especially since we're talking about a composition of functions. So for our domain and codomain, we have f going from a to b, f inverse going from c to d. We've done this before. Now we're gonna say that f inverse of f of x equals x, which means we're taking the composition f inverse circle f. So that since that exists, we have to have b equal to c, right? We do f first, then we do f inverse. The codomain of f has to equal the domain of f inverse, which means now we have f inverse going from b to d. So we have f going from a to b, f inverse going from b to d, but we're going to have the same issue when we reverse that, right? If f is going to ruin the work of f inverse, that means f of f inverse of x is equal to x, which means that F circle F inverse exists, which means that also A has to equal D, right? So if you do F inverse first, and then do F, that means the domain of F inverse has to be the codomain of F. So A equals D. All right, so that means F inverse goes from B to A. So what do we have? Well, here's our definition of inverse. Let F from A to B be a function. We say that F inverse from B to A, right, due to our analysis that we did above, is the inverse of F if we have both of the following. We both have to have, for all x in A, we have to have F inverse of f of x equal to x. And I'm going to use a different variable for y since it's in a different set. So for all y in B, we're going to have f of f inverse of y equal to y. In both of those cases, first one, we're taking an element of A, we're doing f to it, then we're doing f inverse, we're back in A to the same element. For the second one, we start with an element y in B, we do f inverse, then f to it, we're back in B to the same element y. So let's recall our function f. F of x equals 2x plus 3. And remember, we found the inverse, or at least we believe strongly that the inverse was g from r to r given by g of x equals x minus 3 over 2. We should really use the definition to see if that's a real inverse or whether we were just kidding ourselves, right? So we're going to first take g of f of x to see if we get back to x. So let me see. So f of x is equal to 2x plus 3. And for g of 2x plus 3, well, again, I prefer to think of g as an action. That helps when the input is an x. So if we look at g of x, that's x minus 3 over 2. So what we do with x is we subtract 3 from it, and then we divide by 2. So whatever our input is, subtract 3, divide by 2. This time our input is 2x plus 3, so we're going to take 2x plus 3, we're going to subtract 3, and then we're going to divide that whole thing by 2. And hopefully we end up with x at the end. Well, it's looking good so far because the 3 and the negative 3 cancel each other out to give us 2x over 2. And then the 2's cancel out as fractions to give us just plain x. So g of f of x equals x. Halfway there. Now we got to look at f of g of x. Now remember, g of x is x minus 3 over 2, so we want to take f of x minus 3 over 2. Once again, let's think of f as a sequence of actions that we're going to do to our input. F of x is 2x plus 3, which means you take your input, you multiply it by 2, and then you add 3. In this case, our input is x minus 3, so we're going to take x minus 3, multiply it by 2, and then add 3. And then conveniently, in that first term, those 2's cancel on the numerator and denominator to give us x minus 3, so we get x minus 3 plus 3, and then, in a friendly way, that negative 3 and positive 3 cancel each other out, and we just get x. So g of f of x is equal to x, f of g of x is equal to x. That means f inverse of x is actually equal to x minus 3 over 2. There are a few issues we need to figure out before we start celebrating that we understand inverse functions as much as we can. First question we should ask is, do all functions have inverses? Turns out the answer is no. We'll see why in a little bit. And once we know that some functions have inverses and some don't, we got to ask the question, how can we determine which functions have inverses and which functions do not have inverses? Especially if they're functions where it's very difficult to compute the inverses, which you have actually run into in your life as a calculus student. I won't tell you when. How do we figure out how? So if we know that a function's inverse exists, how do we find it? Right? That's another question that we have to ask. And then, if we found an inverse of a function, how do we know there isn't another inverse out there in the world that is also an inverse, right? So how do we know we have just one inverse, or is it possible that we have more than one inverse? I've run out of time to answer those questions in this video. Maybe in one of the other ones. Maybe you should check that out. But first, I suggest that you look at the in-class activities. The name of the PDF file is Introduction to Inverse Functions.